Before I start on the technical side of this session, you may notice some changes. One, probably my face seems a bit bigger and the angle slightly changed, but the big change, well, two I guess, two or three. I have a new whiteboard, much bigger. It's about 2.5 times larger than the previous one, so this is now the third I've tried. The second one had dimensions 1.5 meters by 80 centimeters, so 1.5, 0.8. This one is 2.4 by 1.2, so a lot larger. And what you're seeing here, this area here, is only the upper left, so it's only a quarter of the board. So now that has advantages and disadvantages. Before, the whole board, which took up the whole image, that board was 1.5 by 0.8. This is now 1.2, not 1.5, and this is not 0.8 meters, but 0.6. So this rectangle here is taking up the whole image of the film, so everything should look bigger. That's what I'm reasoning, so it's a hypothesis, so I hope this works out. So I hope that the writing on the board will be larger and hence clearer. That's the plan, that's the hope. I'm becoming increasingly conscious of how critical the readability is of the writing on this whiteboard, because you know, I get feedback from you people, and you're telling me that this is a problem. So you know, thanks for the feedback, and I'm working on it. Now, as part of that process of trying to increase the readability, I was checking through the user guide, the manual of my camcorder, just in case I missed something. I did. I'm not a very practical person. I'm not an engineer type brain at all. And what I missed was there are degrees of high definition. Now, recently I've been filming in high definition, but there are four levels I discovered on my Handycam, my Sony Handycam. There are 4 levels of high definition, and I'm using level 3, like the third lowest. So I will experiment with the top level and see what happens with my son-in-law, presumably. But other people tell me that YouTube don't like these very high definition film and tend to doctor it, to modify it. So you know, I have no idea how this will come out. But expect near future experiments on you know, along these lines of high definition. All right. Now another matter is if this is what you see in the image, but it's only 1/4 of the board. Obviously, that means that for example, to show in the next portion, I'll have to approach the camera, switch off, lower the angle of the camera so that you can see the quarter of the board below it, right, and so on. So for the whole board, there'll be like 1, 2, 3, and 4. So I'll be changing the camera position, the tripod even, for the right half of this big board. Now, another reason for buying the big board is I'm anticipating probably about a year when I get into graduate level, especially math physics. The equations get so long and so many that I will be filling the board with long equations. So I'll need a big board. But that still leaves me with a problem of readability. Like, I have the feeling I'm pushing the limits of what's technologically possible. Well, we'll see. All right. Well, getting back to the nitty-gritty. You remember the last time we had a problem, we had a conceptual problem. We were talking about the free particle, so in a sense it's free to go wherever it wants. So its probability density then anywhere is virtually constant, and that means, so if your probability density is constant, then when you come to normalize the wave function, you get infinity, because the integral of your probability density, your integral's over plus minus infinity, and your probability density is constant, so when you integrate that over infinity, you get infinity. So we've got a conceptual problem. Now, this session, part of it is about trying to address that problem. How can you go about it? Well, one idea is to use something called the Dirac delta function. Now, we've talked about that a bit. Briefly, the Dirac delta function is just a spike, right? Like this. Infinitely thin, infinitely tall, yet the area under this spike is finite, usually 1. Now, in chapter 6, we'll use the Dirac delta function quite a lot. So there's actually an appendix in the text specifically on the Dirac delta function. I think it's appendix C. Yeah, appendix C, the Dirac delta function. You can see that. Okay. So I'll wait till chapter 6 before discussing the details of the mathematics of the Dirac delta function, right? And by using this Dirac delta function, it helps us solving the normalization. When the normalization gives you an infinite value, gives you infinity. So that's a problem. Physics does not like infinities, right? Mathematicians love infinities, but not physicists. The real world is not, well, as far as we know, is not infinite. Right? Okay. All right. Another idea, it may sound a bit far-fetched, it works mathematically at least, conceptually, physically, a bit dicey, but here's the idea. So you assume that the wave equal, the particle, whatever, it's occupying a finite space, right? And this space effectively is not, it doesn't sort of go infinitely in either direction in one dimension, along the x-axis, for example. Instead, imagine this wave equal, this space, this linear space, is in fact closed. It's a circle, well, a loop of some kind, right? So just imagine it's a circle of very large circumference, and call that circumference L, big L. Now you might argue, like for example, in cosmology, the study of the cosmos, the study of the universe, there are models in cosmology where the universe effectively does loop back on itself. When we come to, if you keep following me, when we do general relativity at M1, first year master's level, we'll do models in cosmology on where the universe is infinitely but closed, like it can loop. You can send out a ray of light and it'll just follow curved space and it'll just come back on itself, right? So it's a sort of similar idea here for trying to solve the infinite normalization problem. Okay, so imagine the particles moving on a sort of very large circle, effectively, but of finite, that's the critical word, finite circumference, L. So in other words, if you start at position X, and then you move around this sort of circle, circumference L,